我们上次讲到第几页啊？可以讲到第几页？
课本的238页。
238页。
应该第7页吧。
好，第7页。Okay, so. Okay, let's get on the page number 7. The single EWMA controller. So the EWMA stands for the weighted moving average. So originally it comes from, there's a guy, I think the Crowder, who is a statistician in America. Typically used in SPC domain. Later applied to EPC. EPC is an engineering process. So it represents, this is gamma 0. This is represents since A0 is the initial intercept. That's the initial estimate of the intercept. And alpha is a true value. And beta is a true value of the slope. B is the estimate of the slope. T is a target. So this is represent the initial bias between the expected output and the target, the gamma 0. So between the expected, this is Y and the target. Yeah, let's see. There's do we have a no? No, it doesn't. No. Let me see. Maybe it will be addressed later, I think. Does it show later the gamma? Let me see. YT is yeah. Yeah, let me check. It doesn't. No. Okay. No, it doesn't. Alrighty, and then go back to the slide. So for eliminating the process bias and minimizing the output variance, so this is this objective we like to achieve, which is a bi-objective, the process bias, and minimize the output variance. So it must continuously adjust the process input that is a run-to-run style, and eventually process output will approach the target and remain stable. So the single The EWMA control scheme is the objective of which is to adjust the process input continuously by modifying the model intercept like this. Since this is something we like to update from run to run, B is the estimate by B, and how can we continuously adjust alpha, the estimate the alpha, in order to make the output close to the target as possible. So this provide beta hat is equal to B, is an estimate of the gain, the process gain. And can provide an estimate of the intercept alpha. So once beta hat equal to B, an estimate again, and can provide estimate of the intercept alpha. However, in order to protect against a model drift and other process dynamics. So what is a model drift? This is unidirectional, right? Yeah, this is like a alpha. No, not alpha. This is like a D. The D times T. The D is drifting, right? D can right. And T actually it is the number of batch. Number of the batches. So and other process dynamics. For example, if there's autocorrelation, if there's an autocorrelation, the process other autocorrelation or other is a function relationship, something like that. Then back to here. So the EWMA controllers re-estimate the offset. Re-estimate this one, offset. From run to run, the difference is YT minus BXT minus 1, YT minus BXT minus 1, that is used to estimate the proportion of the alpha at time t. At time t equal to t minus 2, that is equal to this equation YT minus 2 minus beta XT minus 1, XT minus 1, XT minus 2, and so on and so forth, provide an estimate alpha at each sampling point t. So in terms of that, this is the portion we can average those statistics to compute a better estimate. Or even better, we like to use exponentially weighted moving average to give more weight to more recent observation like this. So AT equal to what? YT minus BXT1, YT minus BXT1. That is produced the estimate at time t, AT. And also put on the particular portion of the y on the last estimate, that is at minus 1. 1 minus lambda. And then we factor out lambda. Yeah, it can be doing further the yt minus bxt minus 1 and the 1 minus factor out 1 minus lambda yt minus 1 bxt minus 2 1 minus lambda squared yt minus 2 minus bxt minus 3 and so on and so forth. So we keep doing that, keep going to keep this. Why? Since in terms of the recursion, at minus 1 is replaced by this. At minus 1 is equal to the lambda yt minus 1 minus bt minus 2 1 minus alpha 1 minus lambda at minus 2, and keep doing that and put the recursive relationship into the bracket. So in here. So in semiconductor manufacturing literature, EWMA controllers are sometimes called the bias tuning controller. Called the bias tuning controller since alpha is referred to as the bias term. Like this, this is how the single EWMA can be operated in practice for different. No, this is only example. The example 7.1. Let me see that. No, we don't have. Let me see if we have a real number like this. Okay, later. Okay, suppose that it has been found the beta hat equal to the B equal to the 1.5. We call it the no model mismatch. In this case, no. No model mismatch. What is that? Later. Okay. This is exactly the same. However, we hope the beta hat and the B must be on the same side. Must be greater than 0. Let me put up. So there's a condition. The beta hat times B need to be greater than 0. What is the implication of this equation? Then why the beta hat times B need to be greater than 0? Is any particular is any implication? Is the particular meaning why you need to? Yeah. Beta hat times B greater than 0. It must be. It means both statistics need to have the same sign, right? Sign. If the beta hat is plus, I'm sorry. If beta hat is plus and the B need to be plus as well, right? If the beta hat is negative and the B need to be negative as well, plus plus and minus minus. So they need to have the same sign. If the other is a plus, if the beta hat is plus and however you provide an estimate is negative, no way. It diverges. it diverges. It cannot be used. And the EWMA control cannot be used as if the data head times B is less than 0. So it cannot be used. Peyton, do you understand?
Yes.
Okay, so it's quite important. Then the table 7.1 illustrates the computation required to utilize a single EWMA controller for this parameter for a set of the hypothetic data. It is hypothetic data. As can be seen on the table, the recursive EWMA equation was started from a value of 0, although other value could be used to use this feedback adjustment method. The quality characteristic YT need to be measured. Then EWMA statistic AT is updated from run to run. Finally, the formula XT equal to minus AT divided by B give the subjective value for the controllable factor. In this case, we assume equal to 0. We assume close to 0 as possible. Since in here, we assume it is close to 0. So that's why we can get this equation. Initial estimate A1, A0 is 0. Then there's a no control. Then the Y is equal to 0. You can see that the next estimate is 0.32, like here. We can provide the estimate of that, and the B, we assume this is always 1.5, and we have a XT. Then this is a -1. Hold on, let me see that. B equal 1.5. Let me 0.32. Yeah, like this. We have a 0 right here, and Y equals to 3.25. Y equal to 3.25 minus B equal to 1.5. B equal to 1.5, and x0 is 0. So then this is AT. Then we can get the AT, right? Then once we have a this is a Y1 A1, and we're going to calculate what is X1. So going to compute the X1 since we have the alpha head and with a beta, then we can get this, the point 80, yeah, 0.32. Yeah, let me do the calculation. 0.32 divided by 1.5. Yeah, 0.2. Yeah, hold on, let me do the calculation. I try to find my phone. Hold on. Yeah, I use my cell phone to perform the calculation. Hold on, let me do that. We have this one since we like to calculate what is X1. x1 is minus alpha a1 divided by b. A1 is 0.32. 0.32 divided by the b, and put the minus alpha a1 divided by b is beta in here. B is 1.5. 1.5. Okay, minus 0.2213. Minus 0.213. So this is 22. Once we have it, then recursive to produce a y in here. To produce a y. In here to produce another y2. Once we have a y2, so we can get a2. We have y2. We have x1. So we have a1 as well, so we can get a2. Then get a2. A2 is 0.664. Once we have a2, we have a2. Then we can get x2. We can get the x2 right here. And recursively doing from run to run, doing like that. Do you see that? When you look at this, what do you see? Somehow. Somehow.
Hi.
Is there any trend on the output of y?
逐渐的变小。
Yeah, very good. Close to very good. Getting close to target. Target is equal to 0. Right? Cool. Yeah, very important. Very important. Yeah. So the single controller, EWM controller for this parameter is a set of hypothetical data. So to use this feedback adjustment method, the quality characteristic of YT need to be measured. So then EWMA statistic AT is updated from run to run. Finally, we use a formula minus AT over B. Minus AD over B. Give the subjective value of the controllable factor. We get this one. Once we have this one, then cool. That's so cool. We have it this one, and we have a previous estimate. Then we have a next estimate for the process offset. So this is a run to run. Then so the formula xt equal to minus t over b give the suggested value for the controllable factor in the next run for the time instant t. For time instant t. So if the adjustment is judged adequately by a process engineer, the control factor is also adjusted by a delta xt unit. So like this, yeah, changes. Yeah, that means this is reduce a little bit, reduce a little bit. So you can see that it's only in order to achieve the target, we only apply very a mild adjustment on the output. No, on the input, I'm sorry. Then, yeah, single EWMA controller equivalent to the called the pure I controller. I is an integral. And this is the integral controller. So you can do the recursively into that. So 80, we apply that. This equation applies here. Lambda yt. We do the reparameterization. Yeah, let me see that. Yt minus bxt minus yt, excuse me, yt minus bxt minus 1. Right here, yt minus bxt is equal to the SMA of the at. Right here. Yeah, we have yt plus at minus 1 plus the 1 minus 1 lambda at minus 1. So yeah, so this rearrange into that is equal to lambda yt plus this cancel out. This is plus at minus 1 right here. Then keep doing that. So we have a lambda yt and the lambda yt minus 1 and the lambda t y minus 2 and so on and so forth. So at can be represented this lambda summation ytt. No, this should be t. Should be t minus I. So this is a mistake. This is a mistake. Lambda summation I equal to 1. No, let me see that. T minus 1, t minus 2, 1, 2. Yeah, okay, no problem. There's no mistake. Starting from the t starting y1, y2, y3 until the yt, y1, y2, y3 until the yt. Yeah, this is correct. And process initial estimate A0. Done. So what is this? The current estimate for the process offset is equal to the previous sum of the yt. Yt is the deviation from target. So this is summation. So it is a discrete. This is bingo. Yeah, this kind of the beauty. Yeah, very cool. This is very cool. Okay. Any questions so far? And back to here. I think I'm done. And okay, adjust the process input like this. Okay. Then this is the illustration. Yeah, let us. Let us talk about the illustration. Let me see that. No, does it have the illustration? No. No. Let us do it our way. And the red line, it is a true expected value of the output. Red, RED, RED. Expected output. I'm sorry, output of the process. Is this okay? The red line. And the Y1 had this is the initial estimate A0. Actually, the true estimate is alpha right here. Actually, we don't know the true value of that. This is the alpha. Right? Done. This is the alpha. Yeah, let me see how can we. 佩珍，要怎么样启动可以画画白板？看一下。Yeah, let me see that.
在 PPT 上吗？
Yeah， 可以吗？不行。
你到 PPT 那里。
OK。Yeah. OK。
在那个像书的东西，
书
左边，左边一个，右边，这个，左边，投影片放映的像书的，应该就可以了。
没有，不对啊，你说
右键，
这个投影片放映，阅读检视，
阅读检视，
然后呢？
右键，
然后呢？
没有。
没关系啊，我看一下我要怎么画。Yeah, let me think. Yeah, let me think. Hold on. I try to put some mark. 白板。可是，yeah, I don't know. 白板。Not this one. Alpha.
老师，你可以投影片放映吗？
放什么？
就是最右这个，可以用这个，然后右键。
哪里？
指标选项。
指标选项。
画笔。
Okay. Okay, sure. Okay. Okay, then I want to use 指标选项画笔。I use do not use a black one. Okay. Okay, thank you. So this is cool. So this is alpha, right? Alpha. So the A0, this is the initial. Geez, really ugly. Initial estimate. Hey, come on. So what is that? Good. And no, how can I remove it? Okay, however, then this is a target we like to achieve. So this is the estimate. The A0 is the estimate of alpha. The B is the estimate of the beta. So this is something we like to do. So then initially our so this is target we like to achieve. So this is our initial control initial level of the control factor. Then and however, when we perform, the system has been performed at this level, the output is right here. The white red line is the true response. Then actually our Y is I would like to say, so this is if this is operate in here, and then this is the gamma 0, this is initial estimate. So we expect this is target. If this is a target, the true xt, x0 should be right here. However, we cannot do that. Why? Since we never know the true response is. Then we assume it is right here. However, this is only an estimate. The true response is right here. So this is the initial value. The the gamma 0, then going further. Then what can we do? The best we can do is a horizontal or parallel move to the y1 to y2. This is a y1 to y2. So the b is fixed, and the best we can do is change the intercept. The intercept is, excuse me, okay. So originally we have initial estimate of this one. Then how can we just adjust the intercept from A0 to A1. Okay, so it is horizontally moved to here. Look at that. So this is target we like to achieve, and the line has been shifted from the solid line to the dashed line. Then this is XT. So the interaction point XT. However, we expect the output should achieve the T. Actually, it doesn't. Why? When it is x equal to x1, then the true response is y2 right here. So in here, this is where's that? No, I don't want. Okay, gentlemen. So we assume it is exactly the T now. When we move the x0 to x1, then we expect the output achieve target now. When the x is set at the x equal to x1, the y-axis is right here. So this between this point and this point going to be the gamma 1. This is the bias when t equal to 1. So keep moving around A1, A2, A3, and that will purge, that will force the XT to move around, to change the control factor from run to run, that to make to move the horizontal line up and down in order to achieve the intersection point is close to the optimal, the true response. So that's how the EWMA controller works. Get it? Yeah, like this. Finally, so we move from the x0 finally to x star. So finally, the intersection point exactly match with the true response. The true response is respectively YT, alpha, and beta. This is a true response. True response. Then we have this illustration. Then this is an eye controller. I already showed you. This is eye controller. We're doing that. This is eye controller. Okay. Like this. Provide an estimate to provide an estimate. Then. So the main idea of the EWMA control scheme is for the predetermined B. So that is to say the B got to be of the same sign of the beta. We only need to recursively update the values of the model intercept and the input variable like this. We put a target back, boom, 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 to the target back. YT minus target. So YT minus BXT minus 1. So yeah, we can keep doing that. Where lambda is the discount factor or tuning parameter of the single EWMA that is between 0 and 1. Yeah. Yeah, things are YT minus BXT minus 1. Right here. What? YT, this is equal to that. YT minus beta XT minus 1. This is proportional for the intercept. Like this. This is for the AT. This is AT minus 1, AT minus 2, AT minus 3, AT minus, this is A1, A0. That's why we can correct a collective to represent the whole thing in terms of that. Okay, into an I controller. Okay, then excuse me. We've done this. Okay, then this is illustration. See that we have an illustration. No. Yeah, let me keep reading through this. Then we have a long run and mean square error and so on and so forth. So let me take a look at the illustration first. So this is small discount factor when the lambda only 0.02, very small. So this is a long transient period, very long change. It's a very long transient period. That means it is damping for a while. Really, really a long time to get close to the target. If you use a very large, yeah, you see that fluctuation. See that there's a more smoothing when we using the alpha. However, it takes a long time from the initial to reduce the initial bias to be stable. However, it provides the more smoothing. Better smoothing effects. Like we use a larger lambda 0.98, you can see that it cut the transient period as a minimum as large as possible. So it reduced from the initial to directly into the level we like to achieve. However, you can see that the up and down provide the larger variation compared to the smaller discount factor. So if we apply the larger discount factor, it is shorter. Very shorter transient period. However, it exhibit the larger exhibits the larger variation. Get it? Yeah. So how to choose an appropriate discount factor that can make the process output converge to its target is an important issue. So yeah, we have over at least 50 important paper published in the last 20 years. This is a correctly chosen discount factor should a correctly chosen discount factor should lead the process engineer under control to a stable state. The Ingolfson, published in 1993. So this is a bias corrector as a result of the stability condition for a single EWMA on the SI, CISO, single input, single output. Single input. Input, single. For the CISO. Establish result for the CISO process. The process said to be asymptotically stable if the two conditions are satisfied. First one, expected value of the YT close to T. It is a condition of consistency. Consistency. Yeah. So we are back. Since my internet just off the line for a while. Can you hear me? Hello? Can
Yes.
you? Okay,
Yes.
thank you. Then this limit variance of that need to be smaller than infinity. That means this is limited variances. So this is I'm sorry. Limited variance. Oh, this is the condition of consistency of the stability. Stability. You need to satisfy both conditions. Both conditions. Okay. Okay, we take a break. So please return to class after 10 minutes. Okay, I see you soon. Okay, back to the class. So there's the two conditions that need to be satisfied in order to make a single EWMA is feasible in practice. So this is stability condition of the an SEWMA controller is called the psi. Is equal to the beta over B. So the psi need to be greater than the psi. The 1 minus psi times lambda, the absolute value should less than 1. So it can be written as a form of the lambda. If the lambda equal to close to 1.0, so beta and B should be less than 2. Absolute should be less than 2. So it would be it would rather would like to overestimation. So B we would rather B to be greater than beta, right? Since it need to be less than 2. If the beta is quite large, 10, and B is only 1, the beta 10 and B1 is 10. No, it doesn't. So it doesn't satisfy the stability condition. So in such a case, the B should be greater than beta. So that is we would rather provide an overestimate of beta. We would rather provide a larger estimate, however, need to be of the same side. So the B and beta have if the B and beta have a different sign, then process will always unstable. So when the beta divided over B is less than 2, any value between 0 and 1 of the discount factor can make the process converge to target. Yeah, this is the stability condition. So this is this is a process with shift, and this is a process with the drift. This is uncontrolled output going to deterministic drifting away. Yeah, going to drift away of the target. Okay, I think some of them is too theoretically. Yeah, let me see. The long run mean square error, this deterministic drift. Look at that. The delta T. The delta is delta deterministic drift, right? The delta T, and T is the time period. Time period. like this one, and this is psi equal to beta over b, and we have shown you, yeah, it put in the different style into the state space. However, which will not address this later. So from this, we can obtain the average mean square error, AM. This is a asymptotically mean square error called AMSE. Here, this is AMSE. Long run mean square error, AN. So this word asymptotic, which was not used before. So that recognize the fact that, that for this type of controller, there are tension effects due to the initialization of the EWMA equation that need to be accounted separately from the steady state behavior. So this is for the symptotically mean square error. Yeah, something like that. Finally, it can be approved, can be achieved, can be proved like this. So this is a variance, symptotic variance, and symptotic bias. Like this, like this. The delta is a drift rate. It simply wish to minimize the symptotic mean square error. So if the controller is set up in the in the equation one, then the symptotic mean square error of the closed loop can be proved as the variance. This is the variance, and this is the bias. Okay. So even when there's a no drift, the process really obeys equation number one. The EWMA controller will not achieve the minimum possible variance of the sigma epsilon, like this. Like this. This is psi. Psi we define right here. Psi here is if the psi exactly the same, b equal to the beta equal to the b equal to beta, the psi equal to 1. If it is equal to 1, 1 lambda, and we don't use that if the lambda equal to 0. We don't no. The 1 and then this 1, 2 minus lambda over 2 minus lambda sigma squared. And this is delta over the lambda squared. So okay. So even though there's no drift and the process obey number 1 will not achieve the minimum variance, AMSE is minimized when which imply well, it's not the movement. When the lambda equal to 0, which implies no control, but this result in a divergent offset and divergent quality characteristic will that will trend with a slope equal to the delta. So sometimes it doesn't really help to minimize the delta t. So in such a case, the WEWMA need to be suffices to compensate for the deterministic drift called the double. The one recursion for AT. The second recursion for the there's a two different recursion. So so there's a trade-off when we selecting lambda. So So in such a case, the EWMA will not achieve the minimum possible variance of that due to the tension. Since this is a variance and this is initial bias, we like to minimize both simultaneously. So it's a trade-off. You know that when the common trade-off between the variance and bias minimize when lambda equal to 1. Lambda equal to 1. So since now actually it is not always choose the lambda as close to 1 as possible, and why the variance is minimized for the lambda equal to 0. Lambda equal to 0, so the lambda equal to 0, so this is the variance has been reduced. The variance has been reduced. However, there's a really big tension effect. There's a really high, there's a really large bias. So it is a trade-off. So for a process that drifts considerably, the previous EWMA controller will tend to be significant off target. For this reason, Butler and Stephanie in the 1994, so who presented and advocated as instead a model with a deterministic linear drift in equation 2, they proposed to use a double EWMA controller like this. I hope I can get this. No. Does it show? No, it doesn't show the WWMA. Yeah, let me show you what is the WEWMA. No, it doesn't. No, it doesn't. Okay, later. Okay. Butler, Stephanie, 1994. Okay, let me show you. Butler, Stephanie. $99.94. This one. So this is Butler and Stephanie 1994 supervisory run-to-run control of a polysilicon gate etch using in situ epithermometry. Okay, in situ. The published in the IEEE transaction on semiconductor manufacturing. This is called WEWMA. Okay, then we'd like to address a little bit about how to design procedure for EWMA controller, balance the adjustment and the output variance. Yeah, there's some rule right here. Okay. Okay, then consider the more general disturbance, the NT equal to the delta plus NT minus 1, so NT minus 1. So this is like a random walk, right? The delta is considered the deterministic drift. Deterministic drift, right? And NT minus 1. This is I, right? NT, move the NT minus 1 to the left hand side. This is NT minus 1. This is NT minus. So this is I component. Oh, right. in a Riemann model. This is NT. This is difference data. Difference data. And right here, epsilon t minus theta epsilon t minus 1 is a moving average. This is A1. Moving average of the older one. So it contains the following cases. So if the theta equal to 0, no MA, no deterministic drift, then NT equal to NT minus 1 plus the epsilon t is a Y sequence, epsilon t. And actually it is a random error. Epsilon t is a random error. So if no theta and no delta, NT equal to MT minus 1 plus epsilon t is a random walk, like a drunken man walking out of the bar. And if the theta is equal to 0, there's no moving average. Yeah. And the delta is not equal to 0, then this is a random walk plus deterministic drift. The random walk with the drift, RWD. If the theta, actual value of the theta less than 1, theta is not equal to 0, so the moving average is convertible. It is convertible moving average 1 process. Yeah, it is a convertible. Yeah, it's a convertible moving average 1. Then delta equal to 0. So delta equal to I'm sorry. Delta equal to 0. So this is IMA. NT equal to yes. This is IMA. The IMA is typically used to IMA process in the semiconductor manufacturing. Yeah, it's very frequently used. So-called IMA that is to describe some disturbance that have an influential effect on the output of the semiconductor step, processing step. IMA. And if the theta not equal to 0, actual value is less than 1, and delta is not equal to 0, then this is IMA with drift. This is drift and IMA. If the delta is not equal to 0 with drift and theta equal to 1, theta equal to 1, yeah, it's going to be cancel out. It's close to 0. There's no moving average, so that's going to be the yeah. Let me see that. Theta equal to 1, delta is not equal to 0. Then it's going to be the deterministic train. Let me see that deterministic train. The delta is not equal to 0. Right here, we have a delta. Disturbance is the previous one. This is equal to 0. Yeah. So theta close to 1, it cancel out. So it's a deterministic trend called a DT. If the delta equal to 0, no, and theta is equal to 1, this cancel out. So the next one equal to the previous one. This is only Y sequence. Okay, so there's just so many different forms of the disturbances. And okay. Then we talk about the WEWMA 7.2. 7.2, do we have? Okay, move to the double EWMA controller. Actually in the, yeah, 6 section contain relative more advanced material may be skipped on the first reading. So this is WEWMA. So we assume that the input-output relation of a manufacturing process can be modeled by following equation. The alpha is process offset, process gain. Delta is the deterministic drift. Epsilon t is a random error. Yt observed process output at the run t. Xt is a process input at run t. And the alpha is the intercept. Beta is low. Epsilon t is disturbances. Yeah, epsilon t could be following a Y sequence, can follow be an MA, could be following, yeah, something like something like that. Then then delta is a deterministic drift, the drift rate. So control action. So like this one, we need to, if we don't look into the epsilon t, we move the alpha t, move the beta t, t minus at minus delta t. Target minus the at, a minus the delta t divided by beta equal to the xt, So where this is the first equation? Recursive equation for the at is for the process offset. The second dt lambda to yt, the first yt minus bxt, yt minus the bxt that is used to estimate the alpha t. And yt minus alpha t minus delta t divided by b. Actually, no, minus alpha minus the minus beta t that is used for estimate for the delta t right here. Yt minus beta bxt minus at that is used to estimate the dt. bx and a. Bx and a that is used to estimate delta t, and the yt minus bx that is used to estimate for alpha. Minus for alpha. This is for the alpha for the d. So at is used to estimate the step change. Yeah, for this, the mean change. Mean shift. Step change in mean. So something like to detect is yeah, it could be a ramping effect of a sudden change in mean. Yeah, it could be either way. The deviation, this has been gone of the price. Okay, while dt is used to compensate for the error, dt incurred by at. So the dt is the that is used to compensate for the error incurred by at. This is a process gain, process offset, and therefore it's an estimate for the drifting speed or drifting rate. So dt. So know that if we set a lambda equal to 0, lambda 1 equal to 0, lambda 2 equal to 0, then double EWMA controller will reduce a single EW. No, actually, no. If this is equal to, no, this it's got to be. If set up either one, lambda 1 equal to 0 or lambda 2 equal to 0, W going to be reduced into single EWMA. If the lambda 1 is not 0, lambda 2 equal to 0, this equal to 0. We are not compensated for DT, since now we assume the DT doesn't exist. Then equation 2 going to reduce to a previous process model. Then the single EWMA suffices to perform the control task. Yeah, this is a little bit bizarre, and I think I'm going to skip this a little bit since it doesn't. It has a go too wild about the theory. So let me finish this, and I will skip this. This is too theoretical. The most about the derivation of bias and yeah. No, I don't think I should go for that. I only finished this, then we are done. Okay. Then let me like this. I'm going to draw the scrubbage once again. Yeah. Yeah, I like to use this one. Okay. So this. Okay, you can see that. Okay. No. Okay, so I can see that. So this is expected y1 is expected of the y2, the plus 1 delta plus the 2 delta, since everything going to shift it this way due to the process is ages. Process ages. Okay, it's shifting away this direction. Then let me use a different color. Okay, then, so this is our initial estimate. Then we like to adjust things from the initial recipe x0 going to move to the inward in order to achieve. So we like to, no, I don't see. Where is my point? Where is my mouse point? Okay, okay. Okay, done. So this is target we like to achieve. The target level, so we need to just move inward of the controllable factor. So okay, you can see that this is our initial estimate of the B. The slope is a little bit different. So this is our initial D1, the D0 and the D1. So we move. Yeah, this is not that exactly this. in the different drifting. So this is more going upward. This is going to the northwestern, then northeastern. So use okay. This is going up straightforward. This is going to northeastern. So in order to achieve, so simultaneously we're going to update the AT. So we're going to update the DT as well. So DT is the delta. Actually, we use the delta is unknown. Is drifting away this way. This is drifting up this way. So going to which need to be compensated simultaneous for the intercept and the D as well. So this is an illustration how we work. Since if it doesn't shifting away, single EWMA will suffice. Since it is also shifting away, so we're going to chase. So going to chasing after. We're going chasing after the drifting process. Simultaneously, we're going to compensate the offset in order to compensate the difference between the beta and the B. Also chasing after the moving process, the going that is drifting away from the target. Okay, I think we are done for the. Okay, since the remaining going to be, yeah, this is too advanced. I don't want to bore you since this is my advisor's work, Del Castillo, in 1999 was the drifting the WWMA controller. So, a stability region for the EWMA for the psi equal to 2 if this is model mismatch. So this is going to be the physical region. Psi equal to 2. Psi is defined like this. Psi right here. What is the psi? Psi equal to 2. Yeah, let me give you a definition. So, okay, psi equal to 2, the beta. The beta is 2 and the B equal to 1 when psi equal to 2. This is not that underestimate. If you overestimate it, you will provide a divergent performance. So this is the physical region, and this is design for the WWMA controller balance between the transient and steady state. So this MSD, take the average, so called the VRE. So the measure of the severeness of the expected transient up to the specified round number. So going to skip that. So they try to minimize the average, the variability, and the mean square error of that. And in terms of the solve it, this is a nonlinear optimization, NLP. Method. So this is search the optimal setup for the omega-1 and omega-2 by process engineering according to the nature of the process. So this is called the O bias, the trade-off, the O variances. If the omega equal to 1, this is the omega-1 and omega-1, and then there's no bias, there's an O variance. If the omega-2 equal to 1, this is called the O bias. We're going to reduce the O bias. So if this is both put on the 1, this is called the trade-off between that. How can we solve it? By optimization method. And it just derives some the average, the variances, the average variances. and then it provides some derivation outcome of those equations. Okay, I think I'm done for today, and that's going to be the end of the chapter 7. This is only 1 hour left. I will let the class go a bit earlier, since originally I like to, excuse me. Yeah, let me think. And do we need to go to using time series? Time series control. Okay. I would like to go to the chapter A. However, we only have 1 hour left. Yeah, let me take a quick peek. How many pages? 38. Yeah, I don't think we do have time, since this is a recursively square. No, there's way too many to cover in 1 hour. No. Yeah. Chapter A. No, I don't think. Yeah, this is called a recursively square, the self-tuning controller. Way too many. Self-tuning. Self-tuning. Okay, that's good enough. I'm going to skip chapter A. I let you go. Okay, and okay, before I let you go, now it's almost 10:50. Is there any questions so far for today's class, or about the 10 project? Question. So going to have a demonstration week. Cover demo week for 10 project 2. Question. So
Professor,
yes.
I have a question for the term project.
Yes, go ahead.
I want to ask about the parameter W. The in your description.
W.
Yeah, W parameter in your descriptions.
Hold on. Yeah, let me open that file. Hold on. Give me a minute. Let me open that file. Yeah, let me open that file. Times 2000. Hold on, I gotta have it. Okay. Project. Okay, let me see that W. There's a no W. Where? Which parameter do you refer to? Jun?
Input parameters.
Input parameter.
In the below.
Below?
Yeah, the amount of noise into the system. The second input parameters.
A second input parameter. Lambda? You mean the lambda?
No. The above. The amount of noise into the system.
Okay. You can assume it is with zero mean and the univariate. You can make assumption.
Oh, so it means
okay. This sigma epsilon here. Okay, sigma. Okay, let me see that sigma. Sigma. You can follow the. You see. So I got your normal distribution, 0 and 1. It could be used, yeah, no problem, or it is uniform distribution between the -1 and the 1. Either way. The uniform is, yeah, either way, as long as it's a white sequence, the mean is 0. That will be fine.
Oh, okay.
And any question?
No, just that. Thank you,
Okay.
Professor.
Okay. So in the afternoon, after 4 o'clock, I will be in my office. If any one of you have a question about the term project, you can come to my office. So I only will stay until 5:30. I will leave at 5:30. So since I have a class until 4 o'clock, so I will stay between. There's an open office hour between the 4 o'clock and 5 o'clock in the afternoon. If you have a question, you can come to my office. Okay. Question? No? Hello? No? Jun, is that okay for you?
Yeah, is that okay? Thank you, Professor.
So I thanks for your cooperation. I understand it's a very difficult, very hard for you guys to have an online class like that, since it is quite, my class is so tedious and so full of the mathematics and the derivation. And I really hope I can cover chapter 8 until the end. However, we don't have enough. The time is quite limited. So this is the best we can do. We cover the optimal controller. We covered the EWMA controller. We covered the ARIMA model. Unfortunately, we cannot cover self-tuning. However, I think it is good enough for you in the future if you really want to dedicate yourself to some research that is related to the ARIMA or the control theory. I think you in good shape. Okay, I appreciate all your kindness and your consideration in this very difficult time of the pandemic. I hope you can keep safe, keep healthy all the time until you have been vaccinated, until I'm not quite sure. For the young guys, for you, well, Jun, are you entitled to have a vaccines in Taiwan? Actually, I have no idea since you are foreign student. We are not quite sure. You have, yeah, are you on the list?
And maybe no.
Maybe no. So how can you survive here? Afterward, even though there's the self-developed vaccine is available, then how can you make yourself vaccinated? Could you just call the office of the student affairs to let them know?
Not yet.
Not yet?
Not yet.
Okay,
Not yet.
please call them to let them know I'm the foreign student. I'm also afraid. We are also scared. And then if the vaccine is available, is that possible to also put us on the list to get the vaccinated?
Yeah.
All right.
I just read the news that the foreign students that cannot roll out the vaccines in here for now.
For now, well, for all the young people like you, so the priority is quite low. So now we just supply vaccine to the elder people. Old in Taipei City, this is older than 85 years old. In other city and the township, over the elder people older than 75. So young people will put the very bottom of the list. So you don't worry about that. Even though you get infected, you do not feel anything since you are strong enough. Even yeah, it's kind of sarcastic. All right. So okay, don't worry. Just call the office. So if the vaccine is available for foreign students, you feel free to get the vaccine. All right.
Yeah. Okay. Thank you, Professor.
Okay, thank you. So Pei Zhen, remember, send me the link. All right. Bye-bye.